Boom. Hello and welcome back to Calculus 1 section 3.6, derivatives as rates of change. We already seen the progression, right, the derivation for the derivative from the concept of the secant line, slope of the secant line. So we started by noting that slope is y2 minus y1 over x2 minus x1. Then we upgraded that through pre-calculus, where we replaced y2 with f of x2 and then y1 with f of x1. And we called that one the slope of the secant. And then we went a step further and took the limit of that to create m tangent, which was the limit as x1 went to x2 of f of x2 minus f of x1 divided by x2 minus x1, which led into the whole thing with the derivative. We also said that derivatives measure change. And we can take a look at the slope, understand that it's rise over run. And as you have a linear line and you have 2 points, you have the part where you run and part where you rise. This is known as delta x, which is the x2 minus x1. The delta is read as change. So you would call delta x as change in x, and over here you have delta y, which is y2 minus y1, is when you rise from y1 to y2. So delta y over delta x. And you can frequently see the slope formula being written as delta y over delta x, which says change in y divided by change in x. So all of this stuff is algebra, pre-calculus, and calculus 1 all put together in the same concept. And now we get to use this in our calculations. So this is going to be applied section where we can finally get some meaning to the derivative to talk about velocities in business and other applications. So we start by understanding that the speed is distance divided by time. Now that should be clear because your miles per hour, which is the unit for speed, is equal to the distance in miles computed by the time of the trip in hours, so miles per hour. And you can see that miles divided by hour, that side is the rate. Now our rates are going to split in two. They're going to split in the average rates and the average rates are just basic algebra or pre-calc formulas. Or instantaneous rates, which are going to be derivatives. Now, average ones is going to be average rate is computed over the interval. Instantaneous rate is computed at the point. I'm going to box this. So, travel from point A to point B. I need an example. Someone tell me, how far do you have to drive house to RV? How far? How far, not how long. How far? Miles. 15 miles? 15 miles? And what's the time that it takes to cover that, generally? I'll take 20 minutes, okay? And pretend that I didn't hear the other one. Great. So, from point A to B, we can compute the average speed. Average speed is going to be taking 15 miles and dividing it by 20 minutes. Now, 20 minutes has to be written in hours, so you will have 20 minutes times, you need to cancel minutes, so 1 hour has 60 minutes. You can't see what I'm writing over here, so I'm just going to go here, times 1 hour has 60 minutes. Minutes and minutes would cancel, and you have 1/3. So divided by 1, and that is 45 miles per hour. So average speed, for the speed demon over there, is 45. Now, you can get this if you start in residential, go on 78, spend time on 78 highway, and then get off on the Lamington Road in the back and come back. Yeah, that would work maybe for 45, because speed limit, right? The suggested speed limit on 78 is 65 miles per hour, and the other suggested speed limits are 50 and so on. The trick is that you have to understand that you started your trip when the car was at 0. That's calculated in the average as well, unless you, right, the car was already going to 45 miles per hour, you jump into the car, right, and then at the parking lot, you're still doing 45, you just jump out, right, and the car will take care of the rest. So, so you understand that all of this, maybe you stopped at the stop sign, right? Yes, you do. Okay, good. And then there are red lights as well. So, so there are all these obstructions, right, from you getting to your favorite class ever. Every time when you make a stop, or you get stuck behind knuckles, right? You know what that is. Drive by the car, you see knuckles. There's no one in the car doing 15 miles per hour. All of that calculates in the average. And average takes when you are doing 65 and when you are doing 15 and adds those, and over time smooths it out and say it would be whatever you did with all the stops and speeding and slowdowns would be the same as if you went 45 at all times. So it would be from between point A and point B, you would arrive at exactly the same time. So that's the average. Now, what is instantaneous? What is the derivative? The derivative is actually the instantaneous readout from your speedometer as you drive. You get ticketed for that particular instant. There is a snapshot in time, the instant in time, when cop clocks your speed. It's not, 15-minute snapshot. It's the split-second snapshot. And that is the derivative. You know very well that as you push gas or the brake, the speed on your speedometer instantaneously changes. So at every point in time, there is a speed assigned to that point in time. So if I take with my radar, right, if I take the snapshot of your speed, it will be instantaneous speed, which is the speed of the instant. And that one is the derivative. So we will see later on in which ways these guys are connected. But for now, we think of them as two separate worlds. There is the world of average, which is averaged over time. Think of it as taking a video of an event, right? Whether it's 5-second video or 5-hour video, it's a video that takes time. The derivative measurement is a picture, right? It's a snapshot. It's like a photo finish for horse races. So you have a snapshot. It's a split-second thing. It's once in a, right, at one point there is exactly one thing that happened, and that's it. So that's the derivative. Now, what we can do is we can assign a position function. And that position function, call it s of t, right? Clearly s. My velocity function is going to be v of t, and acceleration function is a of t. So position function is clearly s of t because there is an s in the word position. It's obvious, right? So position function s of t is going to be some kind of a function. You can put whatever. The particle is moving at 3e to the 4t minus x. Minus t. So it's a function of time. This function tells you the position, right? It's going to draw a location on the graph at the given time. Time, let's say you start motion at t equals 0, because that's when the motion started. And then what happened in 1 second, 1.7 seconds, 3 seconds, 10 seconds, 10 minutes, 10 years. You can follow the progression along the path, rather position function, if you know what time you're going to look at it, at the right position function. And then we have velocity function, which is the derivative of the position. So v of t is going to be s prime of t, and in our case, 12e to the 4t minus 1. So this would be the velocity function, and this velocity function will tell you the instantaneous speeds at each point in time. So now, if I say t equals 0, right? At t equals 0, I have a position at 3, right? And then I have the speed is 12. So the motion is starting with me having initial velocity 12 meters per second, miles per hour, whatever you want to, units, whatever need to be. Sorry, not 12, 11. If t is 0, that's 1, so 12 minus 1 is 11. So I would have a position of 3 and maybe 3 feet above the ground, or 3 feet away from the point that we are calculating from, whatever. And then we have a velocity, which would be the calculation when I plug in that. And then we have acceleration function. Which is a of t, which is the first derivative of velocity. And in this case, it would be, or the second derivative of position. And in our case, it's 48 e to the 4t, just for the sake of this example. Now, I am going to box everything except the example. That was terrible. So you have a position function that's given. You can take the first derivative to get velocity function, take the second derivative to get the acceleration function. So now for our example up there, find s of 0, v of 0, and a of 0. Now, when you have this situation of 0, this is initial position, initial case, initial velocity, initial acceleration, everything initial, because it's at 0. That's when everything starts. So in our case, s of 0 is going to be 3e to the 0 minus 0, which is 3. V of 0 is going to be 12e to the 0 minus 1, which is 11. And a of 0, which is acceleration, will be 48. E to the 0, which is 48. Now, if this is, let's say, in feet, and let's say this is in feet per second, and this is in feet per second squared. So now we're going to talk about parabolic motion. So let's do an experiment, and I guess I can only do one trial because I have one marker. So everyone has to pay attention because that's the only trial you get. So this object is going to fly across the classroom, and observe the shape of its motion. It will be downward opening parabola. It doesn't matter how hard I throw. If I do a weak throw, it's going to go down immediately. If I put more strength into it, it's going to go further. It's still going to exhibit a downward parabolic motion, and it's going to hit the ground. Is everyone ready? These guys are ready to duck because I am righty, I'm not lefty, and this is the left arm. So, oh, now you can see them even shrug, right? Don't worry, I'm a professional, all right? If I hit you, you get the prize. You get the marker. The face. All right, so ready, everyone? There you go. Experiment, right? So that's the experiment for today. We all witnessed. Now, I don't care what you throw. Clearly, if you throw a paper, it's not going to work, right? Because of the drag. Yeah, that was your class prep, exactly. If you throw a paper, it's not going to behave that way because of the air resistance, right? And everything else that impacts the paper. But if you are to throw, you know, those of you with iPhones, throw it. See, it's useless garbage anyway. Just It's fine. Just throw it and see, you will see the parabolic motion, right, take place. So, not the calculators though, they're more valuable. So what is the formula? We don't have the method to discover this formula yet, but you are going to learn the method to discover this formula, develop this formula in calculus class. So I'm just going to give you that S of t is negative 1/2 gt squared plus v0 t plus s0. So this is the equation, this is the position function for parabolic motion. Note that the first term is negative t squared, which is negative x squared, which is the parabola that opens that way, right? Are we all green on this? And it must be so because we see it. And a good old day where physics was actually good in education, you could go to the lab and actually do this experiment against the background and then trace the dots on the background and take those dots and put them in the equation and come up with the equation for whatever experiment you did, right? Whatever you threw. It can be an object, can be pencil, can be whatever. Right now, I just click a button on a computer simulation and they say, hey, it's physics. No, it's not. It's garbage. Your physics labs are garbage. I'm happy to see that actually chemistry lab is still okay. All right, and I think that the bio labs are still okay. But physics is absolute disgrace. Sitting in front of a computer screen and doing the simulation for stuff. Someone coded that, all right? And it's a little picture on a screen. That's not how you learn physics. So yeah, they should be redoing that. And it's right there. When I play it back, I don't care. Should. So you have the position function given by this equation. Now we are going to take derivative of this, keeping in mind that we are taking the derivative in respect to t, which is time. So now we have velocity in time is going to be the derivative of the equation above. So 1/2 gt squared plus v0t plus s0. All right, let's take this derivative. So copy negative 1/2 g, that's constant, right? We know that g is a constant of gravity, 9.81 meters per second or 32.2 feet per second, right? So that's the known constant. It's the average one for them. And then what's the derivative of t squared? Very good, right? So 2t. Plus the derivative of t is 1, so just v0, and then plus 0 because s0 is a constant. Recall when I did my experiment with the marker, I had it from, I tossed it from this height. This s is the height from the floor, right? We can rename this s of t as y, and then rename s0 with y0, right? So this is your s of t, and this is your s0. So y would be the height, the elevation, and then t is the progression in time going forward. So now what I have is, when I toss this marker, right, I'm tossing it from the 6 feet height. That's the 6 feet where I tossed it. So that's your s0, and that's constant, right? It's 6. So the derivative of s0 is 0 because it's a constant. Now the derivative of, now v0 is also a constant, which is initial velocity, how fast right? It's all the way there. Experiment number 2. Same height, so for my equation, s0 is the same, which is 6. And the gravity is the same because it's in the same spot, right? So the only difference that I'm going to do now is I'm going to put less v0, which is less of a throw. It's still parabolic motion, It still went and did what it was supposed to do, except it didn't go as far because I had smaller v0. So keeping s0 constant, right? And v0 is constant as well, but it was multiplied by t, so that's why v0 survived in this derivative. So now I have that the velocity in time is equal to half, and 2 will cancel, negative gt plus v0. Those of you who took any physics on any level probably remember the formula v final is v initial plus acceleration times time. That's that equation, except what do you have? Negative g for acceleration, right? So call that a, and you have the same formula. This is where the formulas come from. No one actually, thought of these formulas. It's a simple mathematical construct of the reality. And now we have acceleration function, which is the derivative of our velocity of negative gt plus v0, and that derivative is negative g. So we know that acceleration in the parabolic motion is just gravity. In order for me to change this experiment and have a different type of acceleration involved, I would have to put little jet propulsion engines on my marker, right? And then I fire that up and throw it. And in that case, there will be another thing to propel the motion other than what I did with v0 and what gravity is doing with acceleration, right? So if I want to change from this free fall gravity controlled, and you can see it's only gravity here because we took the derivatives and mathematically came up to the acceleration function at all times, and the only acceleration that deals with this example is gravity. So these are the three equations that you see for parabolic motion. And now we want to use these equations to calculate cool things. For instance, what was the maximum height that the marker reached when I tossed it? Well, that's a really cool question, as long as we remember that when you throw things up in the air, they stop at the highest point and then they come back, right? You can figure out at which time that occurs, the maximum height, because the velocity is 0. So you can set the middle equation to 0 to find the time of the maximum height, and then use that time in the first equation up there to see the location, right? So let's say that we toss a ball or whatever else, toss an elephant, or doesn't matter, toss whatever with position function s of t equals to 19t squared plus 3t minus 4. All right? And the question is max height. Well, you will take the derivative of s to find the velocity. So that's going to be 38t plus 3. And then you will set this thing equal to 0. Let's change this to minus so we don't get negative signs. Whatever. And now you set this equal to 0 to calculate time. So time is equal to 3 over 38. Call it seconds, whatever. Why are we setting it equal to 0? Because object stops at the maximum height. When you throw something up, if you are not if you're not tossing it so high to do the escape velocity, right? To go off the planet, like a rocket, for instance. If you toss anything else, then it will, because the gravity is pulling downwards. Gravity is not pulling downwards, the curvature of space and time and all these things, but let's call it simply gravity pulls down. It doesn't. The object will go up and it will be slowing down and slowing down and slowing down. It will stop and then go back. So at that highest point, object stopped, which means velocity equals 0, so the derivative equals 0 at that point. You can calculate at what time that happens because, as you can see the equation over there, t is the only unknown. Now I have time at which max height occurs. Figure out what's s of 3 over 38, and you're done. So that's going to be 19 times 3 over 38 squared minus 3 times 3 over 38 minus 4. 19 will cancel one of the 38s, so you get 9 over 38 times 2 minus 9 over 38 minus 4 times 38 over 38 to get the common denominator. And now I need to multiply everywhere by 2. So that's 38 times 2 is 76. So that's 9 minus I need times 2 over here to get, so that's 18. And then minus I need another times 2 over here to get 76. So that's 38 double double double. So that's 38, that's a 76, that's 152. So this is first, second, and one more, 304. So 304. There you go. And when we get all of these guys, this is negative 9, so negative 300, and wow. Not too happy with, with the answer, but whatever. I just made up random numbers. So that will be max height. I just had, you know, bad numbers. So, oh, because I used minus 4, that means that I tossed the object 4 under the, yeah. So if I put the plus there, that doesn't change any calculations other than at the very end. So if I put the plus here, then we'll have a nice value. So that will be minus 9, so 295. That's much better. Max height, let's say feet. Right. So here is the entire problem. Exchange of goodies. All right. Toss the ball. No, it wasn't a ball. Let's say toss a marker, right? From 4 feet, somewhere over here. So from 4 feet height, and right. So what is the maximum height? The maximum height that the marker reaches was somewhere over here, right? And that's that number. You will deal a lot with, you already dealt a lot with growth models. in your pre-calculus course. Yes?
When you took the first derivative and you have t equals, do you know what does that mean? Equals 0?
This?
No, when you put it to 0, you know what the
Oh, I don't know why I put it. This is set to 0 because max height is velocity equals 0. That's the concept. So set it to 0 because max height is velocity 0. That's what happened. Again, look.
So that's why it's up there.
Yeah.
That's the equation.
You see, when it reached this location, it stopped. So velocity is 0. The speed of the marker is 0, and then it started picking up speed going down. Okay? Good. Growth models. One of the most basic models for population growth, right, is the model that says that population at any time t is initial population times e to the kt. This is one of the basic population growth models. And you learned how to deal with these models in your pre-calculus class. They tell you that the initial population for, I don't know, rabbits is 500. So P0, 500 rabbits. And then if you waited, I don't know, you waited, let's say, 3 years, there was 600 rabbits. You can use this information to come up with the formula for the population growth for this colony of 500 rabbits that became 600 rabbits. So what we do is we know that the P0 is this, so you will say P of t is equal to 500 e to the kt, and then the next data point is 600 is equal to 500 e to the 3k, right? Because the time is 3 years. You have 600 rabbits. And as you can see, the only unknown quantity is k in this case. So you have 6/5 is equal to e to the 3k when you divide 500 both sides. You ln both sides to get rid of e. And then you use your abacus to compute ln of 6/5. Which is 0.1823, keep 4 decimals at least, equals to 3k, and then k is equal to, divide this by 3, and get 0.0608. No, 0.77. 4 significant. 0.77. There you go. 1, 2, 3, 4 significant figures. Guys, you have the model for this rabbit population. You start with 500 e to the 0.06077 t. This is the model for the rabbit population with the specs that I gave you up there. You decide to create a rabbit habitat. You dump 500 rabbits that you have into that habitat, and you already know your P0. You wait 3 years, you come in, and you sit down, and you count the rabbits. 1, 2, 3, 4, 5, 6, 600, right? So you have these data points from your measurements and observations. I don't care if you're going to work with bacteria, or you're going to work with rabbits, or people, or whales, whatever you do, right? You can do the measurement of how many units you have. And then the rest is the standard mathematical procedure to come up with a model which predicts the future of that species. Now, this is the worst possible model you can have because it's unrealistic. It tells us that the population will go to infinity if you take the limit of this, right? We also know the exponential graph looks like that. So we know this is not a good model. But you know what? At some, for some time, 0 to maybe 10 years, it might be good, And then after that, it's going to be terrible for the upper part. Because, again, we all know what happens when the resources are scarce, right? Something called competition for resources. And it's nothing like Olympics or whatever. What they say, good game, good game. No. It's mine. So now, what do I want to calculate with this? Well, I want to calculate the instantaneous change. So, instantaneous change, I want to know what is the instantaneous change in the year 4. Now, that question is analogous to me asking how many new rabbits are we adding? Well, rabbits are adding in the year 4. That's the instantaneous change. Because it is just like one snapshot in time, that 1 year. Well, it's a big snapshot, but yeah. Because we are looking at this population change per year. You can look at it per month, per day, per hour, right? But the thing is that if we are looking at per year, then the snapshot is done per years. So 1 year, yes, it's a long time, right? It's not a snapshot like the split second, but still. So what do I need? I need the derivative. The derivative is copy the constant times drop down the exponent. That was that a business. And then keep everything the same. And now you have 500 times this to calculate. And we get that the population, derivative of population is 30.385 e to the 0.06077t. That's the derivative. Now I can answer P of 4. P of 4 is you plug in 4 into the equation. And that will give you the number of rabbits added to the population in year 4. It gives you the change for the year 4. So we have times e raised to the 0.0677 times 4. 39.8, which is 40 rabbits. Please don't add 0.8 of a rabbit. That's all right. So the population grows by 40 in year 4. In year 4. Now, so this calculation means in year 4, 40 rabbits are added to the entire population. Not to be confused with P of 4. P of 4 is the number of rabbits, of all rabbits in, right, year 4, and that better be more than 600. So we are going to have 500 e to the 0.06077 times 4. 637.6. So 638 rabbits. Oh, S here. Rabbits. This is the number of all rabbits, the number of the population, the number of the entire rabbit population. So the derivative will calculate only the number of new rabbits added. These are the little rabbits hopping around, all right? 40. And P of 4 is the total amount of rabbits that you have in year 4. Yes?
So why is it if it's even that we have a year 2 600 rabbits, we know that in year 4 we add 40, why our number is slightly different?
Rounding. Yes, it's rounding. It's rounding. And again, you also have to understand that all of these will be actually estimates when you start working. All of these are estimates. Because are you really going to go to Habitat and actually tag and count every rabbit up to 600, right? So there are also estimates on top of this. But I mean, this gives us a pretty good idea. You know, even if it's 10 rabbits off, it still gives us a pretty good idea. And you can actually, guys, I mean, I encourage this. Go play with the human population on Earth with these kind of things, because the data is available on Google. Google the population in 1980, use that as a population 0. Google a population in 2000, right, which is t is equal to 20, and then try to estimate today's population. Try to see how many new people we add every year. Now remember that the number of that is going to be much more because it's new minus dead. Because population is constantly growing. So we are adding more than what's dying. Clearly, right, the advances in medical field and everything else. So you can actually, go and look at the real problems and things that we are computing in the field. Now, clearly, you take Calc2, there is a better equation. You take differential equations, much more content and better content there, and then you can actually specialize in these things. You get courses on those kind of stuff, right? So it depends on if you have interest in it or not. The last application that I want to do for our rates of change is business application, so where we are going to take a look at the cost of producing a product, and we're going to take a look at the difference between average cost and marginal cost and marginal is the derivative. So let's take a look at business. Business application. And we're talking about the cost. So, if you want to go and research one of the gods of understanding of this concept, you'll obviously take a look at Elon Musk. Created so many of these companies and startups, and each one of them was major and each one is successful. Clearly, you can be as brilliant as you want. If you are not well-rounded and educated in other areas, your one kind of thing, strength, is pretty much meaningless. It's been almost 100 years, well, 80 years since Tesla died. And arguably one of the biggest minds we ever had on the planet, where all of our technology today, everything we have, is powered and it's his concepts. He died in poverty, all right, living in a hotel room in New York. So one of the most brilliant minds that ever existed on the planet. We are talking about all of the electrical work, the alternating currents, transformers, generators, electrical motors, everything that exists that powers everything we have today, including radio, television, wireless transmission, charging, and everything else, all done by his concepts, plus thousands of things that we still don't understand what the hell it is, or in his notes and things. Died in poverty, and it took years to for human race to understand who he was, and we still don't, right? What was he lacking? He was lacking everything else but that. He was socially awkward, very awkward, was not a good writer, and terrible for business. I mean, everyone exploited him any way they wanted, especially Edison. Stole half of his stuff and inventions and presented them as their own, and other companies, not just it. So when you have someone who's just one-track mind, not good. So anytime when an engineering student tells me, "Oh, I hate writing," right? Yeah, you're useless. I'm sorry, but you're useless to any company, because if you can't present your idea, and if you can't explain because you hate communications or you hate speaking in public or in a meeting, you're useless. And that's the end of the story, because you can't market your skills and your ideas, and no one has any good from it. Your job is to learn how to write and speak, and then you can present your ideas and yourself and be successful. So Musk, all of it, right? He reads. That's the one trait that all of the billionaires have. Read every day, a lot, and everything. So, yes, he was engineering major. Yes, he does computer science. Yes, he does all of these kind of things, but he reads and he learns from books how to run the business, so he can create all of these businesses from nothing and make them into some of the most profitable and most important things that are done on the planet today. So business application, cost analysis. I don't care that most of you are engineers, right, or not. Stuff like this, you have to understand if you want to have a business or develop a product, or even work in an environment where, you know, you develop something but it costs too much and obviously it's useless, right? Try to make a new phone whose production cost is going to be about, you know, $8,000 per unit. $8,000 just to produce it. 60% markup on that to sell. What's the price on the phone? No one's going to buy it. Well, 6 people will on the planet, and that's it. So you have to have sense for business and these things, even if you are engineering. So let's take a look at the average and marginal cost. First, I'm going to say over here, average cost is the cost with C with the bar on top, is the cost function divided by the number of units produced. So, the more units produced, the cost of the production is lower, actually, and the cost of the product is, right? So what can you buy this marker for? Few cents, right? 10 cents, 20 cents, 30 cents, whatever it is. There's not much to it in terms of the design. A lot of utility, obviously, but right, that's also the part in the whole calculating the price. But the cost. Now imagine one painting. One painting. It took someone 10 months to do it. There are paintings that are produced over a much longer period of time. And then you go in a gallery and you walk around and you look at a painting and it's cost, you know, $10,000. And you go, what? Are you insane? It's just like color on the canvas. Yeah, but it took 10 months. So that's $1,000 per month. You can't live off of $1,000 a month. But then again, look at the cost. You made one. It's not a production where that painting came out, you know, you produced 50 at the same time. The print is going to cost less. But if there is one painting and that's it, well, obviously it should cost much more than that. So average cost is when you take the cost function and you divide by the number of units produced. Now, cost function, this is not a part of the book, but it's good to know, is going to be variable cost plus fixed cost. Some other things, but this is it. A variable cost. Variable cost would be the materials and all of the things that vary from, for instance, if I order a box full of raw material, a truckload of full of material, or the train load of full of raw material to make something. Clearly, the more you order, the less it costs. So variable cost would be the cost of materials and things like that. You have a fixed cost. The fixed cost would be setting up the production. I need a machine. I'm not carving this out of plastic with my knife, right? There's a machine that builds this. That machine is purchased and installed once, and it's going to make millions of these. That would go into the fixed cost. There is also bill for electricity, salaries for people that are working, and everything else, maintenance, insurance, and owner's yacht, right? All of these kind of things are there in the cost of the product. So cost function is the variable cost plus the fixed cost, and in calculus class, that is given to you. So I'm going to give you C of X. So you don't have to worry about the subtleties of what's what. So the average cost is going to be the cost function divided by how many units you made. Marginal cost is marginal cost is going to be the derivative. So marginal cost is C prime of X. It's just the derivative. I guess the business world couldn't handle the word derivative, so they said marginal. All right, just change the name. All right. So these are the two, and now we're going to take a look at the example. They give this one in the books. It doesn't matter. Cost function to produce something between 0 and 1,000 units. So I don't know, some exotic car or a boat or whatever you would make 1,000 and then just shut the production down. Definitely not these markers, okay? So cost is given as negative 0.02 x squared plus 50x plus 100 if we are making 1,000 units. They want us to figure things out in terms of marginal cost, average cost, and then compute those and interpret those at 100 units and 900 units. So let's find the average cost first. Average cost is C bar. And you get that when you divide your cost function by the number of units. So you're dividing by x. So we get negative 0.02 x plus 50 plus 100 over x. So this is your average cost function. Marginal cost is just c prime of x, and that is the derivative, so negative 0.04x plus 50. Remember that the derivative of 100 is a 0, because constant. So it's very simple to obtain these two, average cost and marginal cost. Now they're asking us to compute these at 100 and at 900. So let's compute the average cost of making 100 units. Well, we plug in 100 everywhere. So that's negative 0.02 times 100 plus 50 plus 100 over 100. That gives us negative 2 plus 50 plus 1, and we get 49. 49 what? Well, cost is in which units? What's the unit for cost? Dollars. So this is going to be dollars per unit. Now, if you are making 100 units, on average, it costs you 49 bucks to make each unit. Now, you have to know this when you are setting up production in a business, because if you set up your production and business and everything, and you never calculated any of these things, and you go on the market and charge 49 or 48 or 45 to undercut someone else, are you making profit? No, you're not even breaking even, right? Because your average cost is 49. If you're selling stuff for 45, you're technically paying out of your pocket. Clearly, do yourself a favor. Don't start up anything if you're not going to spend a long time doing these kind of things to begin with. And then you have the C prime, which is the marginal cost. And that is going to be negative 0.04 times 100 plus 50. One morning. And that is going to be negative 4 plus 50. And you see that that one is $46 per unit. Now, what is this number? What is this number, 46? We understand that the 49 is the average of all units make. So it's like 49, on average, 49 per unit. What's the 46? Which one? The 100th one, right? Yes. So, on average, each costs 49 bucks to make. All right? Let's talk about the... See, I need a new thing. So I'm in the market for this. Let's say it costs $49 to produce this on average. But the calculation below, the marginal calculation, tells us that actually to make the 100th one is 46. And that should be clear. The first unit produced ever is the most expensive one. You see that? Imagine if I need to produce this and I spend $150,000 to set up a machine that is going to produce this. How much does it cost me to produce the first unit? $150,000, right? Because it has to suck up all of the cost of setting up production and everything else, plus all the salaries, plus all the electricity and bills and everything else, and the raw materials for the unit. So it's more than $150,000, right? So the first unit, extremely expensive. The more you produce, the cost distributes over number of units that will be sold, and you can track individual cost of making each unit. You can go calculate for 67, 135, and so on. We are going to compute now for 900 because they are asking us to. So what is the cost the average cost for 900 units. Well, it's negative 0.02 times 900 plus 50 plus 100 over 900. That is going to be negative 2, so that's 18. And then plus 50. And then plus this is 1 over 9. 1 over 9 is 0.1111 forever, right? So 11 cents. Is it? Yeah, 11 cents. Because 1 divided by 10 would be 10 cents. Yeah, it's good enough. Oh, yes, negative 18, thank you. Negative 18, yes. Drop that negative. So now what do I have? 18, and this is 32. So 32 and 11 cents. Dollars per unit. And the marginal cost at 900 is negative 0.04 times 900 plus 50. And that is going to be negative 36 plus 50 is equal to $14 per unit. It has to be clear. The average cost, the more I produce, over here I produced only 100 units, over here I produced 900 units, the average cost went from 49 to 32. That's on average. And then 46 down to 14. So the cost of producing 100 unit is 46. The cost of producing 900 unit is only 14. Okay. That's crazy good. So now you should go and watch some of those Elon Musk interviews when he's talking about how he figured out to start, Tesla with the cars, and why he started with Model S, and then, Roadster first, right? But why he started with the Model S, and what business models clearly to him this is, a napkin. Works this out in 15 minutes and say, yep. So now just put $1 billion into it and done. Not a problem. That's where calculus kicks in. That's where calculus kicks in, and it really helps you understand which way these things go. So the difference between the average and instantaneous, that is the highlight of this lecture, this section. And the average is dragged through the time. It takes all of the situation that we are considering, smooths it out, averages out, gives one answer. Marginal or instantaneous or the derivative gives the individual snapshot in time. You determine the length of that time, whether it's a split second or a year. And as you can see, it measures the instantaneous change. So it measures, in this case, measures the cost, right, to be at $14 per unit at 900. Now you can go and calculate for 1,000, and all of these numbers are going to be even lower. The more units you produce, the less. Now you have to obviously take courses that are designed for this, to understand if you produce way too much of something, to understand the supply-demand curves and everything else, so that you are not oversaturating the market. We have the huge plague of the cars. They're everywhere in terms of, right? And they can't even sell them all. So that is something that, but then you go far back in the past, there was when it came out, they couldn't produce enough. There were waiting lists for 6 months for people. And now, obviously, Tesla Model 3, there are hundreds of thousands of people that gave the $1,000 pledge to get the Tesla Model 3, and clearly they're struggling to keep up the production, but I'll get there. So these are the things that you can consider. And that's that. Take the break. After the break, we talk about the most important section of your calculus career, the chain rule. See you soon.